about how to find roots of cubic polynomials without using the grapher first. In order to do that, let's take a look at one with the grapher. Here is 2x cubed plus 5x squared minus 14x plus 3, and I want you to notice the root that I've got highlighted here at 1/2, or 3/2. That's the root. So the root of this cubic was 3/2, and I want you to just notice those two numbers that we have here. The 3 and the 2 come from the polynomial itself. This is not a coincidence. This is always going to happen. And the rule that says so has a name. It's called the rational zero theorem, or I call it the rational roots theorem because I like alliteration. I don't want you to get too caught up in the language of this theorem. It sounds more confusing than it really is. It's not a very tricky idea. For any polynomial function, and this is the part, like, don't get too caught up in this. This is just some polynomial where I don't have any numbers. I don't know what degree it is. I don't know what the coefficients are. I don't know how many terms there are. It doesn't matter. This is just any polynomial where a sub 0 is the lead coefficient, this thing out here, and a sub n is the constant at the end. That's all that really matters to us. If you're going to have a rational zero, or rational root, then the numerator of your rational root, that p, it has to be a factor of the constant at the end, and the denominator has to be a factor of the lead coefficient. That's the rational roots theorem. It's not necessary that the numerator is exactly the 3 and exactly the 2. That was sort of a coincidence here. It doesn't have to be exactly 3 and 2. But it does have to be a factor of the last constant and a factor of the first coefficient. For example, 2x cubed plus 3x squared minus 17x plus 12 has a root at 3/2 also. Notice how the numerator is 3. The constant to the end is not 3, but 3 is a factor of 12. And the 2, the denominator, is a factor of 2. And so that's why the one root can be at 3/2. Now that we know this, we don't need the grapher to find the first root and then use synthetic division to take out all the root and find the quadratic and solve to find the other roots. We can do it on our own. What we're going to do is make a list. Move that out of the way. What we're going to do is make a list of all the possible rational zeros. And it is important that you do set this up, consistently. So we are going to make a list of all the possible numerators, which are going to be all the possible factors of 9, which is 1, 3, and 9. And all the possible denominators are all the factors of 2, 1 or 2. And then we're going to make a list of all the possible combinations. Remember, it's the numerator comes from the constant, the denominator comes from the lead coefficient. So it could be 1/1, 3/1, 9/1, or 1/2, 3/2, or 9/2. But there's a slight catch which makes things a little bit less fun here. And that is that 1 times 9 and 3 times 3 aren't the only ways to multiply to 9. You could also use -1 and -9, or -3 times -3. So the numerators and denominators both, there's a little bit of uncertainty of whether they're positive or negative. It could be one of each. So each of my possible numbers might be a positive number or a negative number. So in reality, there are 12 possibilities here. And what we're going to have to do is check them till we find one that works, which I understand sounds a little bit crappy of an idea, but there is a way you can shorten your work by using a little bit of brain power. So here's what the thought process goes. We know that this is a 2x cubed. It's a cubic function with a positive lead coefficient. So we know that the end behavior is going to be up to the right and down to the left. We know that. We also know that because the 9 is the constant at the end, we also know that there is a y-intercept at 0, 9. There has to be. And so the dots that we're going to connect are literally dots that we're going to connect. The function has to go from that y-intercept to the end behavior in some way. I don't know what kind of ups and downs it has in between, but it's got to go from up at 9, and as we move off to the left, it's got to go down towards negative infinity, which means somewhere in the middle there has to be an x-intercept, which tells me when I'm doing my guessing, I'm going to try to guess negative numbers first. That's my thought process. It's up to you to decide which negative number you want to try first. I'm going to go with what I think is the easiest to do the math for, which is negative 1. So I'm going to try synthetic division with negative 1. And we will see if negative 1 is a root. Negative 11 and negative 2, negative 13 and negative times negative 1, add the 12 and the 13. And you might be noticing, like, I don't think so, this isn't going to work. But I'm going to finish it because even though it didn't end with 0, and even though x plus 1 is not a factor, x equals negative 1 is not a root, this negative 16 is actually important to me. Because we learned a couple of classes ago something called the remainder theorem, that when you try to divide a polynomial by x plus 1, which remember is x minus a, x minus negative 1, the remainder you get is the same thing as f of a, or in this case, f of negative 1, which tells me that the graph will go through the point negative 1, comma, negative 16. And so what I've done there is, we're talking about connecting the dots before. Now, not only do I know that connecting the dots is going to lead to a negative root, I know that there has to be a root between 0 and 1. Because somewhere between here and here, somewhere in that little section, there has to be an x-intercept, because my graph is going from positive to negative, or negative to positive, if we're going from left to right. Which means, process of elimination, I don't have that many numbers I have to check. On my list, there's only one number that's between negative 1 and negative 0, so that's going to be the number I try next. It's not guaranteed to work, because in theory, whatever root is happening in here could be irrational, so maybe it's not negative 1/2, but it's certainly my best possible guess. And if I do multiply 2 times negative 1/2, notice every time the denominator here is going to be even, it's going to cancel out that 2. So as long as I keep getting even numbers there, I'm in good shape. And negative 1/2 times 18 is negative 9. So I got my 0, we got what we wanted, which leaves me with a quadratic to solve. I do want you to remember to look for GCFs. It's easy to forget, but it's so helpful if you can divide by that 2 first. And then in the end, what happens here is we actually end up with a double root here. X minus 3 squared equals 0. So when I take the square root of both sides, there's really no such thing as plus minus 0. It's just 0. And so I actually only have one other root at 3. It's from a double root. So if I wanted to graph this, which, I do, there would be a root at negative 1/2, another root at 3, which is a double root, and there's a pretty good sketch of a polynomial. Our final answer, because the directions were to find the zeros, actually, now I'm looking at it, the directions weren't to find all the zeros. It only asked me for the rational zeros, but in this case, all of them are rational. So I will write all 3 of them. Even though that 3, it's really, I'm listing 2 numbers because the 3 is a double root. And that's the final answer. I will show you one more thing about this before we end the video. And just a little bit of a trick you can use, which is not actually helpful that often, but it's very easy to check for, so it's definitely worth thinking about. Here's another one. We're going to try and find the rational roots of this one. We will start exactly the same way as before by listing the possible numerators. There aren't that many numbers that go into 10. Listing the possible denominators. There are even fewer numbers that go into 7. And then making the combinations to list the fractions. I'll list the whole numbers first, and then the fractions. There's no right or wrong way to make this list, as long as you include everything. And you might be saying, well, what about the plus or minus signs? Well, in this case, if we take a look at this expression there, all of those terms are positive, all of them. Which means if I plug a positive number in for x, I'm going to get positive from 7x cubed, and a positive from 16x squared, and a positive from 39, and a positive from 10. There's no way all of those numbers add up to 0. That can't happen. So there is no way that any roots on this graph are going to be positive. Any roots that there are have to be negative. Have to be. Or imaginary. Which means when I make my list, I'm not going to write plus or minus for each of these. I'm going to say my roots have to be negative. So I'm only going to list these 8 possibilities instead of the whole big list of 16 possibilities. Which might not be the biggest deal in the world, but every little bit helps when we're doing process of elimination. So keep that in mind when you try and do the work here.